Hello everybody and welcome. Thank you for joining us online today. You're part of the over 200 people worldwide who have registered to this webcast powered by YOL Development and System Plus Consulting. It is entitled 3D Packaging is Breaking New Ground. Our today's session will last about 40 minutes with 30 minutes presentation and 15 minutes of Q&A. My name is David Jordan, and I am Global Sales Support and Coordinator for YOL Development. To shortly introduce YOL Development, we are part of the YOL group of companies, which provides marketing, technology, and strategy consulting, media, and corporate finance services. We support industrial companies, investors, and R&D organizations worldwide to help them understand markets and follow technology trends to develop their business. So back to this event. Before we get started, let me give you some basic information on this webcast. During all the webcasts, you can ask questions using the Ask Question button. Question will be answered at the end of the session, and we will answer as many questions as we can today. Remaining questions will be answered by email later on. Concerning the materials, please note that the presentations are already available and downloadable in the resources section of the platform. Within 24 hours, you will receive an email with the link to the recorded webcast session. So, I am pleased to welcome today our two keynote speakers. Xavier Xu, Technology and Market Package Assembly and Substrate from the Semiconductor, Memory and Computing Division from YOL Development, as well as Dr. Stéphane Elisabeth, Expert Cost Analysis at System Plus Consulting. Both of them joined forces to provide you a better understanding of today's 2.5D and 3D packaging market and evolution. So, let's start with the presentation. Xavier, the floor is yours.
David, for the excellent introduction. Hello everyone. Good morning, good afternoon, and evening, depending where you're calling in from to watch this webcast. My name is Xavier, and today I'm going to present to you the market and technology trends in 3D packaging. In the presentation proper, I would like to run through with you the outline of this webcast. So the key topic here is 3D packaging is breaking new ground, and we have bring up four main chapters. Market technology and trends, where we'll be talking about the appreciation of semiconductor packaging in general, the semiconductor industry trend, the 3D, 2.5D packaging value, market drivers, landscape, and the hybrid bonding, 3D SoC, IP landscape. And after that, we'll be focused on the key technology and the cost analysis for 2.5D packaging, 3D packaging, 2.5D and 3D imaging technology. This will be deep dive and presented by my fellow colleague, Stefan. And next, we have the market forecast to give you the perspective of the valuation in 3D packaging, how the total packaging revenue comes about, and the breakdown into its end markets. And finally, we'll wrap up with a conclusion. On to the presentation proper. So, in this semiconductor industry trend, we know that Moore's Law has guided the global industry in semiconductor for the past decades, improving both performance and cost through node scaling. So you can see that after 2002, the industry has been consolidating extensively, and there's limitation in scaling. Has disrupted the companies competing in this business. Currently, it is an oligopoly market with a handful of key players remaining. So this is mainly due to the cost of building a new facility. For example, in 5 nanometer production, the cost expected is about 5 billion, which is 5 times more than 20 nanometer fab back in 2012. So you can see that such a steep investment cost is the main barrier and key reason why more players are falling out of this technology scaling race. So, presently, the industry is seeking alternatives for the design and the manufacturing latest of the system on chip SoC using system in package chiplet based approach by leveraging of different advanced packaging technologies to have a mixture of both the latest and the most matured nodes inside this package. So this way, you know, the cost, the time to market can be reduced, while at the same time economically enhance the system performance. So this is a combined roadmap of a 3D interconnect density versus the technology node trend. So if you look at this chart, you can see that there's, apart from the gray color scale, where you can see that's on the right, on the gray scale, which is onto the right side of the graph of the y-axis in the technology node, you can see that the scaling continues since 1970 from 10 micrometer all the way to expected 3 nanometer by 2025. And as this scaling continues, you can look at the value on the 3D interconnect on the left side, 3D interconnect density on the left side of the chart. You can see that there's two types of 3D density. One, which is the orange line, is a node scaling only. That means this is the system level 3D density with only node scaling. Whereas if you have 3D and 2.5D scaling added value into this scaling, you can see the value of 3D 2.5D packaging value increases the overall 3D density. So, you know, while the front-end scaling remains a work in progress in the background, the industry now is diligently utilizing advanced packaging technology to multiply, have a multi-chip, virtual chips in a single package, and heterogeneous integration is what they are looking at. So 3D 2.5D can extend the 3D interconnect density, and you know, node scaling coupled with this 3D packaging can bring the overall system level to the next level, and perhaps this could be the new Moore's law at the system level. Then this is the value of the 3D 2.5D packaging value we're looking at. So now, moving on to the market drivers trend, right, for 3D 2.5D, you can see the market driver includes like these various list of devices by I/O density and timeline, and bracket by the different types of technology like hybrid bonding, embedded silicon bridge, TSV, 2.5D interposers, and UHDFO, which is ultra high density fan-out. So this adoption of this market driver is really mainly due to the adoption of like cloud and edge computing, which increase this higher premium performance in the end system units, like in cloud computing, networking, high performance devices, in consumer personal computing, and gaming. So there's a strong progress in this aspect, and the advanced packaging technologies, as mentioned just now, can help to bring these devices to the next level of I/O density and functional integration in high-end performance applications. So these technologies have, you know, become increasingly vital to the modern digital age technology, and it's really creating a lot of market opportunities for us. So if you look clearly, like before 2019, which is left side of the chart, you can see that, out of the graph, you can see that there has been a very good traction of the 3D stack DRAM, HBM, FPGA being commercialized. And it revolves around like a CPU, central processing unit, GPU, graphical processing unit, etc. Applications linked with processor cores. And we also have memory, SSD, different memory blocks and graphics. So if you look at like 2020, forward-looking, there will be more complexity, more synergy between different packaging technologies, which the details will be covered by my fellow colleague, Stefan. But I can see that there will be a lot of synergy in this aspect. Like for example, TSMC and Intel are working on hybrid bonding to package a departition SoC with front-end capabilities. And such is the value they're trying to bring to the table at this point in time. And you can see that Intel is also venturing into exascale GPU with their trademark name called Porte-Ficure. So you can see that in general, the 3D 2.5D packaging is accelerating towards new technical breakthroughs for better performing capability. All right, moving on to the landscape of 3D 2.5D packaging. In this slide, we have put together the mapping of players based on technology, and not only that, we have also mapped out the space of this technology by I/O pitch and I/O density, right? So starting from the left to right, bottom to up, we have ultra high density fan-out, 2.5D interposers, 3D stack memories, TSV micro bumps, embedded silicon bridge, and also at the far bottom right, you can see, far top right, you can see hybrid bonding bumpless. So in general, you notice that there's a middle end zone between the front end and back end where bumping and packaging can be executed on wafer level, hence can be reached by the OSATs, foundry, and IDMs because all of them have able to enter this arena. And OSAT is scaling further since the package can start earlier in the manufacturing chain at wafer level, which is the middle end. However, for the next generation stacking, it involves both the front end and back end capabilities. Big players like Intel, TSMC, Samsung have successfully tapped into this higher end domain, and they're achieving faster time to market than the OSATs at an unprecedented scale. So in this next slide here, we have the IP landscape of hybrid bonding 3D SoC. So as we know, hybrid bonding and 3D SoC are projected to be the future of 3D packaging. And it perhaps does not come as a surprise that more and more companies are trying to secure IP protection through patenting in this field. So interest in this area has been rising. Based on the IP filings, you can see in hybrid bonding and 3D SoC, TSMC is leading the way, followed by YMTC, Xperi, SMC, Sony, Samsung, IBM, Lefty, etc. So we know that, so in a nutshell, this company has now they have filed for IP and they have started to use the 3D SoC as a weapon to exclude other manufacturers from hybrid bonding 3D SoC production. And perhaps they're generating royalties through licensing. So this is the IP landscape trends that we are looking at right now. And this next part of the presentation on key technology, focus, and cost analysis, I'll hand over to my colleague, Stefan, who is an expert in this area, and he will cover deeply in this chapter on technology and cost. Stefan?
Thank you, Fabi. Hi, everyone. I'm Stefan Elizabeth, cost analyst at System Plus Consulting, and I'm in charge in RF and advanced packaging. And today I will present you some recent observations made by System Plus on 3D packaging. So let's begin with the 2.D packaging approach that is mainly used in the industry. So here is the list of the complete reverse costing report that at System Plus we provide. And since 2015, we published several of them. And as you can see, since 2017, we have followed the rising of NVIDIA with the HPC GPU. And now we are in progress in the analysis of the latest Ampere A100. And in this review, I will give you some insight on this last one. So the first 2.5D packaging that we have seen on the market came from AMD with a 4-stack of HBM1 memory from SK Hynix. And this system was integrated on a passive interposer for the first time. And back in the day, the process used was first based on chip-on-chip process. Chip-on-wafer started in 2017 with both AMD and NVIDIA, and it's still using in 2020. If we take a look at the dimension, since 2017, NVIDIA released 3 HPC GPU, and all of them are integrated on the same footprint, even in 2020. And we can see that the P100 and the V100 share the same memory architecture. In the P100, NVIDIA chose to release 2 different memory architecture, one with 16 gigabyte HBM2 and one with 12. And to do that, they integrated a silicon filler with the size of the HBM stack to reduce the volume of the memory and also to maintain a reliable structure. And in a V100, we have seen a smaller silicon filler at the sides of the devices with only 2 metal layers on it. We think that it was for reinforce the structure and also maybe to reduce the warpage. And in 2020, NVIDIA has done the same thing as for the P100. It only contains 5 stacks of memory, HBM2, and the 6th is only a piece of silicon that is added in the molding. So in this type of devices, the interposer is the 2.5D enabler in the configuration. Back in 2015, first interposer was quite large. It was, and the HBM and the CPU was placed by using chip-on-chip process, as I said before. But the interposer was not molding. Based on the size, we have seen that the interposer was already larger than the reticle limit, that is about 800 millimeter square. But the implementation of the implemented circuit was in the reticle limit. So in this way, AMD has the support of the silicon interposer for the dies, but the interconnection between them was only at the bottom of the die. And in 2017, by reducing the number of HBM stack and by using HBM2 with 8 memory dies, the company achieves an interposer in the reticle, the use of the interposer in the reticle limit. But NVIDIA, in the same year, choosing a different approach by doing directly an interposer larger than the reticle limit. And to bypass this issue, TSMC, the CoWoS manufacturer in this case, has developed an approach that uses 2 paths of lithography and a stitching area on the interposer. And they push the limit of the reticle limit to 1.5. And today, with the latest devices in the A100, we assume that the reticle limit has been pushed further at 1.75. So our first results for now is based on the tomographic analysis of the devices. First interesting fact is the absence, as I said before, the absence of the 6th HBM stack in this configuration. In this place, there is only a piece of silicon that is on top of it. But looking at the tomographic footprint of the interposer, we can see that the interposer and also the GPU has 6 I/O banks on it. But in the actual configuration, only 5 are activated. Maybe in the future iteration of the GPU, the 6th bank of memory could be filled to provide higher memory in these devices. For now on, the analysis is still ongoing, and we will provide further analysis soon. Now, to give an example of comparison, I show you here the graph extracted from a 5-year presentation, and we can see that in the split of the I/O pitch versus the I/O density, the 2.5D with interposer has a wider application in terms of I/O than ultra-high density fan-out. But there is a region between both that both technology are in the battle. And it is where high-performance switches, for example, could be either using interposer or fan-out technology for the packaging. And here, the cost could be one of the criteria of choice. So we choose a high-performance switches from NEFOS to apply the comparison. On one side, it's using the CoWoS solution with an interposer, and for one side, is using RDL from fan-out technology from CSLC. So here we show a simple cost estimation of both structures. And the most interesting part that we can see on the cost breakdown is that for both packaging, the main portion of the cost is on the consumable. For the info packaging on substrate, all came from the consumable, all the consumable to realize the RDL routing. And for the CoWoS solution, it came from the interposer that I count as a consumable, and from the assembly. So finally, when we take a look at the packaging cost for the components, we can see that the CoWoS solution is around 20% higher cost than the info solution. We could estimate that that's why NEFOS goes for the info in this case. Of interposer technology that we have seen on the market recently is the Intel Foveros solution. And for the first time, it has been integrated in a consumer devices. So here, the use of the interposer allows to connect a CPU die manufacturer in 10 nanometer technology node to a PCB substrate with, on top of it, we have DRAM memory. And in this case, the interposer has been made active. So in this way, all the interface blocks are integrated at higher technology node than the CPU. And in this way, it's a real cost saving for the devices. One of the issue that Intel has to make an effort in the design was for the power delivery and signal path through the interposer. Indeed, in the actual devices, the power delivery was made with several TSV per ST4 band. As you can see here, at the right, you have a signal TSV that is single, and at the left, you have the power delivery, a TSV power delivery example by 4. And in this interposer, the group could be up to 12 TSV per bump. And so, by using this group, the path is direct from the C4 bumps at the bottom of the interposer to the Foveros die die-to-die interconnect with the CPU. Also, for the manufacturing of the TSV, Intel chose the via middle configuration, unlike passive interposer, where it's usually via first. And by using the via middle configuration, Intel is able to provide power delivery gate on top of the TSV, or the power delivery TSV, to connect the CPU. So now we have seen the major 2.5D technology packaging, and now we move to the 3D one. So here is the list also of the reverse costing report that we as System-Plus provide. I had in this graph also the YMTC 3D NAND X-stacking report that showed the heat rebonding application to the memory. Because since 2015, we just see HBM devices that stack memory die using microbump. And now is the first time that hybrid bonding is used in memory. And we expect in 2021 maybe the integration of HBM2E that will improve the memory speed and also density in the HPC GPU. So to begin with the memory die stacking, I will show you here the evolution that we have seen in the HPC GPU HBM memory evolution. So at the left, you can see the first one with the AMD Radeon Fury X. And after that, the memory has moved to HBM2. So for the first, we have SK Hynix implementation, and this one was using, for the microbump, for example, copper and nickel. And for Samsung, we have seen that it's mainly nickel since the first introduction, and even today. But with the HBM2, we have seen a very improvement in terms of technology. For example, we have seen an improvement of the die density that was multiplied by 1.6 from HBM, and also an improvement of the memory efficiency. And the second one, the second interesting way to stack dies is the hybrid bonding. And today we heard a lot about this technology, but its implementation was done a few years ago, mainly for CMOS image sensor. And the latest application of this technology was made in a 3-stack CES from Sony that was using a stacking of an ESP, so image signal processing, with a DRAM memory and a textile array. And in this way, Sony was able to really increase the speed of the signal processing treatment, and also a very compact CES in a very small footprint. But these devices was just using an old TSV implementation that was a TSV last process. And that we know that the main recent interconnection between stack dies is copper-copper bonding. And in this one is used in the latest memory released by YMTC. This one is used copper-copper bonding and TSV last process for the link to the top. And hybrid bonding is a real game changing in this case. Here is relative level of die density, die size, active area, and also effective memory for different 64-layer 3D NAND memory. And we choose the reference as the Toshiba 3D NAND memory that use traditional floor plan. And as you can see here, the YMTC devices has the highest level of die density with the smallest, one of the smallest die size, and it's given the highest level of effective memory area. And as it's the first devices on the market that use hybrid bonding, we could expect a very improvement in the future for other manufacturers with the use of this technology. And now we expect that we will see a merging of several actual integration that is already available on the market to provide higher flexibility and quicker time to market by having a cost-effective solution. And here, for example, we have Intel that is working on co-inhib solution that will couple the 3D stacking technology that they implement with the Foveros face-to-face interconnection with the inhib technology that embeds bridge in PCB. By doing that, the company will be able to really use multiple type of die on the base on the active based die that could really improve the speed of the data processing, and also allows the heterogeneous architecture. C is also working on this type of integration, but based on SOIC solution. And we think that and for me, it goes beyond Intel solution, because with hybrid bonding, we could have a lower Z height solution in this case, and also the interconnection between the dies could be less with parasitic influences, and also the foundry will be the only player for the assembly of the different die. And this will be done with the hybrid bonding in one side. For example, one from the solution from YMTC, and the other one will be the CoWoS that is already used since several years. So thank you, everyone. And now we will move to the market forecast with Javier again.
Hello, everyone, again. Thank you, Stefan, for the highly valuable technical presentation. Now I will cover the market forecast. So before I go deep dive into the figure numbers, I would like to present to you and bring your attention to how we segment the market, because not all 3D, 2.5D integration packaging are focused on the higher-end segment. In my market forecast, I'm focused on the high-end segment. So as you can see, it's being broken down into high-end segment on the left side and mid-low-end segment on the right side. So in high-end market segment, we are focused on HPC, networking, gaming, whereas on the mid-low-end side, they are focused more on the sensing and lighting. So we define high-end market segment 3D, 2.5D packaging where an application is less sensitive cost, but requires smaller footprint in addition to high performance and higher reliability. Okay, now I would like to also come to this slide where I present to you the total packaging revenue in the 3D, 2.5D. The market is valued at 0.8 billion in 2019 and is projected to reach 4.7 billion by 2025 with a CAGR growth of 32% from 2019 to 2025. So this is a very strong growth, and it's pretty much attributed to the fact that high-end packaging has become an 3D, 2.5D packaging has become an essential part of the semiconductor packaging supply chain, which allows the integration of diverse dies, chips across multiple process nodes, achieving similar, if not better, performance than monolithic SoC, extending Moore's law at system level. So, this has led to the emergence of giant players like Intel, Samsung, and TSMC by end market. We can see that the biggest market revenue of this 3D, 2.5D packaging comes from telecom infrastructure, where it's accounting to more than 50% from 2019 to 2025 market share. So among these prominent digital age demands, these packaging drivers are really increasing the implementation and interest in the end system units in cloud computing, networking, let's see, HPC, consumer devices, personal computing, and gaming. So these trends are paving the way for 3D, 2.5D packaging market opportunities. And in addition to that, you can see that the growth in the mobile and consumer is increasing aggressively because of the adoption in the Internet of Things, mobile connection, smart objects, these opportunities present itself for more expansion at device level. So they all need a big, fast memory that interacts quickly with the processing units. For example, in the advanced computing for gaming, we have a TSV deployed in 3D segment DRAMs and HBMs, and GPUs is being equipped with this high-speed memory for high-performance gaming. So, and more recently, Apple has released an upgrade iMac Pro that integrates the AMD Radeon GPU Vega 10. And YMTC, as mentioned by Stefan just now, we know that they are using hybrid bonding in their hard disks. And of course, Intel's Foveros is being adopted in laptops and consumer devices. So we are seeing this new penetration of 3D, 2.5D packaging into these various markets, and also not to miss out the automotive and mobility. It's also adopting because of artificial intelligence, sensing and robotics, high-end sensing and robotics in the vehicles. So I've come to the conclusion of this presentation. So in general, you can see that 3D 2.5D packaging has become essential of the semiconductor in general. It's viewed as a system level's Moore's law because of its ability to create additional value for 3D interconnect density. So the various market drivers and adoptions are evidently observed in cloud computing, networking, HPC, and various devices as mentioned here. And it will continue in this trend because a lot of it, they need far more intelligent, multifaceted devices to achieve that end demand. So there is an extensive trend towards finer pitch and more functionality with 3D 2.5D integration. So this is actually a dramatic shift in the fundamental of this semiconductor supply chain. You can see that leading companies like TSMC, YMTC, SMC, Sony, Samsung, and IBM are starting to place high priority on 3D SoC and hybrid bonding IP strategy, right? So the market valuation, as mentioned, is growing at a strong growth of above 32% from 2019 to 2025. And this is growing from a market size of 0.8 billion to 4.7 billion by 2025. So these are our takeaways for this webcast, and thank you.
Thank you very much, Xavier. So thank you very much for your thorough market and technical presentation. We will now conclude this webcast with the Q&A session, and we will answer as many questions as time allows us. We will follow up via email for the remaining questions. So let's begin with some questions for you, Xavier. First question.
Sure.
If future demand is truly digital, how will 3D packaging evolution be like in the next few years?
Firstly, thank you, David. This is a super good question. I think it is no longer a matter of if, how, because technology has already changed the way we entertain ourselves, socialize, consume data, and exchange and produce information. So there's no denying now the future of technology will continue to revolutionize our lives digitally. So I think, like, in terms of evolution in 3D packaging, for a start, I think we will be expecting more front-end and back-end innovation and technology breakthroughs in this market space. Because now, as you know, we have observed that ultra-high density fan-out is competing with 2.5D silicon interposer for the departitioning of logic dies for high-end servers. And within 3D stack memories like HBM, 3DS, 3D NAND, they're starting to face pressure from hybrid bonding technology. And, you know, the embedded silicon bridge that's used to replace a big silicon interposer to save package level consumable costs. This is, you know, used as a way to save costs and critically, precisely create channel for die-to-die communication. So we have like this future generation packaging that aims for a higher density in 3D IC system level or finer pitch of below 10 micrometer, and that is typically done by view as the next generation is hybrid bonding, right? So we know that leading suppliers like TSMC, YMTC, Samsung, Intel are all targeting this. They want to provide the leading edge hybrid bonding solutions, and this could be perhaps the true inflection point between semiconductor and packaging world. Thank you.
Thank you, Xavier. Another question for you. Why are front-end players supplying packaging solution?
So this is not an easy question to answer, but I'll try my best to provide you some perspectives. So the fact is that the industry trend in big data, edge computing, large bandwidth, and form factors have entirely transformed the value within semiconductor supply chain. They're distributing the new workload and challenges from front end to back end, trickling down the high end value. So this new mode of system level value needed from the back end has pushed packaging into a new high end innovative regime. And presently, you know, even some products presently at the moment would not be achievable in the market, commercialized without advanced packaging, 3D packaging solutions, right? So it is evident that the industry has transformed into digital-centric era, and advanced packaging is playing a bigger role than ever before. And that is recognizing the fact that advanced packaging is going to be bigger than before. And this is why the front-end players are involved, like Global Foundry, TSMC, Intel, and Samsung, because they've been investing and been involved in advanced packaging for more than a decade. But it's only recently that we observe a strong interest from the front-end players with advanced packaging, because reality is that Moore's law has been slowing down. The scaling has come to a hardly cost-effective regime. So there will be a limited number of end system applications that have sufficiently high profit margins to cover the increased costs for the next scale of advanced nodes. So front-end players are developing 2.5D integration solution, 3D technologies to match the functionality and the performance of a monolithic SoC by connecting chips or chiplets into a single package. That will help to provide more value at a more cost-effective level. So in the short, front-end players are strategically motivated to unlock innovation and deliver high-end performance by combining the front-end and back-end best-in-class practices and capabilities economically to improve the product-level performance, power, and form factor. So that is why front-end players are supplying packaging solutions. Thank you.
Thank you very much. A long and detailed answer. Thank you, Xavier. So let's go to Stefan. We have some questions for you. The first one. In the future of 3D packaging, what will be the killer portion of the cost?
Thank you, David. It's not a really simple question to ask, but I think we could learn from our devices on the market now to see what will be in the future the real issue in the cost. For example, I think the first one will be maybe for the wafer thinning. We know that today it's one of the issue in terms of die stacking, because we need to have a very low profile in the low Z height in the device to be able to have several die stacking in, for example, for the HBM. And I think it's one of the killer one. The second one, maybe with the rising of the hybrid bonding, could be the wafer pick and place. Indeed, for the copper bonding, we know that there could be some misalignment that today play on the yield, and for the future, it could be also one of the cost killer. And yeah, I think it's the two main ones from now.
Okay, another question for you, Stefan. What are the main specifications for choosing between hybrid bonding and chiplet technologies?
Yeah, another complicated one. I think it could be to be short. It could be the simplicity, also the flexibility, and finally the time to market. For example, in the chiplet application, we know that it's simple and also flexible, because you just have to put several dies together on top of an interconnect device to be able to have a very compact system in package solution. And by using different technology nodes, you will be able to really be cost effective. But one of the main concern in this type of application, it could came from the interconnect, because you have to play with all the interface to be able to have a very high performance interconnection between all of the dies, and the design the design of this interconnect will have to be we have to work on. But at the end, it could provide a very quick time-to-market solution. On the other hand, in the hybrid bonding, the way that it's today implemented is that you have the same die all over the wafer, and you assemble two wafers together before the singulation. And in this way, it narrows the heterogeneous design. But I think that in the future, for example, TSMC will provide some solution to enhance this heterogeneous design, and provide a solution like with flexibility, like for the chiplet application. But maybe it will suffer for maybe a little bit longer time to market in this case. So thank you for your question.
Thanks a lot for your exhaustive answer, Stéphane. So the webcast is ending now. Do not hesitate to contact us if you have additional information, if you need additional information, or if you have, we will follow up with you via email later on. And you will receive tomorrow the link to the recorded session to the webcast. So please also feel free to share our presentation with whom will benefit from our data and analysis. Finally, please let me remind you that you can find all our market research and teardown reports, as well as our monitor and tracks on our website, micronews.com. Thank you very much for joining us today. Have a good day. Goodbye.